Testing, testing, 1, 2, 3, testing, testing. Ah, testing! Checking for latency. Okay. Hello. Welcome. Good morning to everybody in the... Oh yeah, I have to bring the chat up on my phone. Sorry about this stream saying that it was for 1MD3 for the majority of the intro scene. It was... I have to remember to click that. It doesn't do it automatically. Oh, there we go. Alright! Thank you all. This is one of my red spotted ones, which is... This is one of my personal favorites, actually. Anyway, yes, over the course of the semester, you will have an opportunity to see a large variety of your professor's bow ties. Anyway, so, we will eventually start on the first slide of our first topic, but we still have a little bit to get through with respect to the syllabus. Yes, yeah, it's crazy, because, like, when the, when I looked at the videos from Tuesday again, and, you know, just to make sure that I wasn't umming and ahhing too much, I know how frustrating it is to listen to somebody who's umming and ahhing so as much as I sometimes have a tendency to. Hi! But, you know, the audio was desynchronized by about half a second, which was gross and unusual. So, right, let's get to it. Okay, that's a good way to get banned for spamming, okay? Okay, so, I think I downloaded the syllabus, did I? Oh, yeah, it's in this tab. Okay, so, over the course of the previous lecture, we got through most of the syllabus. We didn't quite get to... I think we talked about the textbook. So, I'll start from here. The textbook is Deedle and Deedle's How to Program C 8th edition. There you go. 10th edition does exist. It doesn't really matter which one you get, if you want to get it. If you get, like, I actually have the 5th edition here, which was what I used when I was an undergraduate, and it is, I think, almost exactly as good as the 8th edition, so do not feel under any obligation to get the most recent version of the textbook, should you choose to do so. There will be weekly readings. I believe the chapters correspond between the two textbooks, so it shouldn't be that bad. The weekly readings are not compulsory. You don't have to do them. The purpose is to deepen your understanding. So, like, I think the ebook format of How to Program C 8th edition is $100 on Amazon, so I don't know if the bookstore can do better than that. Probably not, but, you know, bless them, they try. So, getting assistance. There are a lot of people in this class this semester. So, we have this Piazza Forum, which has been set up. I will show it to you for a moment. Piazza is a sort of collaborative forum question-asking environment where a person can ask a question and you may receive answers from either your peers or one of us, the instructional team. This is going to be our first point of contact if you have any questions about the course. We'll be monitoring it reasonably closely. So, that's good. If you have problems that are of a more personal nature, you know, Piazza is anonymized, so you don't have to worry about that aspect of it. But if you have something of a more personal nature that you'd like to inquire with either the TAs or myself about, you're welcome to do so. Incidentally, we're still trying to sort out that third TA slot. Man, it has been a hassle. So, you guys are second-year students, so I don't imagine that I have to bang the academic integrity drum too loudly. Hardly? That hardly matters. You are expected to exhibit honesty and use ethical behavior in all aspects of the learning process. Academic credentials you earn are rooted in principles of honesty and academic integrity. Academic dishonesty is to knowingly act or fail to act in a way that results or could result in unearned academic credit or advantage. Blah, 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 blah. It is your duty to know what constitutes academic integrity. That is your responsibility as the student. Some examples are plagiarism, the submission of work that is not one's own as one's own; improper collaboration in group work, also improper collaboration in single work; copying or using unauthorized aids in tests or examinations, i.e., writing the answers on your wrist; allowing your work to be copied by another student. People who allow their work to be copied are just as culpable for academic dishonesty as the people who did the copying. Submitting for academic credit work that has already been submitted for academic credit. This is one that a lot of people don't even realize is in that, but it is. If you have taken this class previously, and you resubmit all of the same assignments that you submitted the last time, despite the fact that you failed the course and are retaking the course, so, you might want to do different assignments, but if you submit the old ones, that's considered academic dishonesty. Automatic plagiarism detection. In this course, we will be using a web-based surface, MOS, stands for Measure of Software Similarity, to interrogate the authenticity and ownership of student-submitted work. MOS is a system developed specifically for detecting plagiarism in programming code and is tuned to the specific ways code is plagiarized. MOS generates a plagiarism report in which pairs of submissions are given a similarity score, the highest of which are tabulated into a report. Submissions which have a high degree of similarity are then examined manually for plagiarism by myself or the TAs, and dealt with accordingly. Do not be fooled. Contrary to public opinion, a person's code is as unique to them as an essay would be, and that is almost even more true for something as low level as C. The argument, well, there's only one way to solve a problem anyways, will be dealt with by the swift wings and iron zero-giving fist of electronic justice. Students who do not wish their work to be submitted through the plagiarism detection software must inform the instructor before the assignment is due. No penalty will be assigned to a student who does not submit the work to the plagiarism detection software. All submitted work is subject to normal verification that standards of academic integrity have been upheld. Example, online search, other software, etc. For more information about McMaster's use of Turnitin.com, please go to www.mcmaster.ca/academic integrity. Ha! There you go. So, I'll run through the rest of this stuff reasonably quickly so that we can actually get to the course. Courses with an online element. Obviously, Piazza is a third-party system. If you do not wish your information to be given to a third-party system, you are well within your right not to use it. So, nobody really cares that Avenue has it. Yeah. So anyway, just keep in mind that the internet is the internet, and that third-party people might be taking your stuff, and using it for nefarious marketing purposes. Should you choose to engage with it, but if you choose to engage with it, there are benefits to that as well. So there you go. Online proctoring. Some courses may use online proctoring software for tests and exams. This software may require the students to turn on their video cameras, present identification, monitor and record their computer activities, and or lock/restrict their browser or other applications/software during tests or exams. This software may be required to be installed before the test/exam begins. Don't worry about online proctoring for this course. We're going to be doing things in take-home format, so we don't have to worry too much about. I'm not going to be creepily watching you while you write your tests. What if it happens to be similar with nuanced differences? And no, I'm not repeating that. So if we suspect plagiarism, what happens is the case that you have plagiarized will be presented to you and the person that we have detected that you have plagiarized from. You are at that point going to be permitted to make a case, a case for the defense, as it were. So it's impossible to answer a question like that without seeing the specifics of a specific situation. But shall we say, you will be, if you are dinged for plagiarism, you will be given a chance to defend yourself. Generally speaking, the penalty for a first offense is a 0 on whatever evaluation the plagiarism occurs on. So don't do it on the exam, or the tests, or the assignments. Don't do it anywhere, but don't do it particularly on things that are worth more. Yeah. So yeah, just don't cheat. Simple. That's the simple way to not have to worry about plagiarism, is just don't cheat. Anyway, here's some other boilerplate stuff. Expectations of student conduct. You guys right now are under the auspices of the Student Rights and Responsibilities, the Code of Student Rights and Responsibilities, whether you realize it or not. Your online interactions with myself, the TAs, your other students, are subject to the stipulations in the Code of Conduct. This means, basically, don't be a jerk, don't harass people, don't call people names, just be cool, be a cool person, in general. Yeah. Academic accommodations for students with disabilities. Students who require academic accommodation must contact Student Accessibility Services to make arrangements with a program coordinator. Academic accommodations must be arranged for each term of study. Student Accessibility Services can be contacted by phone, extension 28652, or by email. For further information, consult blah, 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 blah. Give me 2 seconds. There. Academic accommodation for religious, indigenous, or spiritual observances. Students requiring academic accommodation based on religious, indigenous, or spiritual observances should follow the procedures set out in the RISO policy. Students requiring a RISO accommodation should submit their request to their faculty office, normally within 10 working days of the beginning of term, in which they anticipate a need for accommodation, or to the registrar's office prior to their examinations. So, for those of you who have, religious holidays on a due date, for instance, something like that, all of the due dates are known ahead of time, so you should be able to just scan through the Section 4, see if there are any conflicts with any religious, indigenous, or spiritual observances, and submit the appropriate paperwork accordingly. Copyright and recording. Students are advised that lectures, demonstrations, performances, and any other course material provided by an instructor include copyright-protected works. The Copyright Act and copyright law protect every original, literary, dramatic, musical, and artistic work, including lectures by university instructors. The recording of lectures, tutorials, and other methods of instruction may occur during a course. Like this right now. Recording may be done by either the instructor for the purpose of authorized distribution or by a student for the purpose of personal study. Students should be aware that their voice and/or image may be recorded by others during the class. Please speak with the instructor if this is a concern for you. This is not a concern for you necessarily, unless you're very worried about your chat thing, the live chat feed being recorded. If it bothers you that people will see your chat, then I don't know what to say except email me or ask a question on Piazza about the question that you have after the case. Extreme circumstances. The university reserves the right to change deadlines and dates, etc., etc. You know, if there's a second global deadly pandemic that happens that causes us to change all of the dates again, we reserve the right to do so. And the online participation disclaimer, blah, 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 already talked about it, etc., etc. Okay, that's the syllabus. Thank you very much. If you have any questions about the course, the manner in which things are going to go, please put them in the chat now, and I will answer them. I'll give you a moment to think of questions that you might have for me while I very, very slowly and laboriously bring up our first set of lecture slides. Okay, let's get to it, shall we? One quick note about these lecture slides before we get into it. These circles at the top not only indicate our position in the lecture, but they are also clickable links to be able to navigate the lectures themselves. So that's kind of useful. We will... Oh, I do have a question. Do you have any guides, tutorials for downloading Jupyter and its kernels? I do not have any of that material. For the downloading and installation of Jupyter, check out the Anaconda distribution website. There should be instructions there on how to get Anaconda that has Jupyter in it. With respect to the kernels, there are instructions for installation on each of those kernels on their respective GitHub pages. So by the second year of a degree such as this one, you should begin to understand that you will occasionally be required to follow instructions on someone's GitHub page, so this will be good practice. No, I don't have any materials like that. I'm having a tough enough time just trying to keep on top of generating the slides for this course, just, you know, so we're clear about things. So, Software Engineering 2MP3 Programming for Mechatronics. All of you lovely roboticists out there. This is the introduction to the course. It is a 34-slide presentation. I am NCC Moore. I have two middle names. They both start with the letter C. This is McMaster University in the fall of 2020. This set of slides and all future sets of slides have been adapted from See How to Program 8th Edition by Deedle and Deedle. When I wrote that phrase, I thought I was going to be doing a much more direct adaptation of the existing lecture slides than I ended up doing. These are quite a bit revised from what has been presented in the textbook. Can you use other IDEs or text editors and copy the final code into Jupyter? Yeah, so long as you actually execute the code and make sure that it actually works. Good. Yeah, you can write the code in whatever you want. Yeah. In fact, one of the topics in next week's tutorials is going to be how to get VS Code to do C for you. So there you go. Personally, when I show you guys a C program, I'm probably going to just use my Linux terminal here. So, okay, I just wanted to say one more thing. I'm currently just about finished with topic 2. I think yeah, I just have to proof it. Topic 2, in case you're wondering where this is going. Topic 1 is approximately compiled from Chapter 1 in the textbook. Chapter 2, however, composes chapters 2, 3, and 4 of the textbook. And I know that sounds like a lot, but the textbook is designed for people who know no programming whatsoever. And, there's a lot of time wasted, shall we say. So let's actually get into it. We're going to talk about hardware versus software, data representations, the C programming language, the C standard library, other C-based languages, quick overview, and the process of development in C. One other thing to note about these slides before we continue, just a disclaimer. I have made these slides, but I don't know how well they will correspond to the weeks as laid out in the course. It's kind of just going to take as much time as it takes to get through each set of slides. As long as we keep going, we'll cover all of the topics that we need to cover. So I'm not sure if this is a 2-lecture slideshow or a 3-lecture slideshow. I just don't know. It's kind of that's the risk that you run when you're making slides for a course that are brand spanking new. This is also the first time that I've done such a thing for a course, so it also is attributable slightly to me and me not knowing how long it takes to say things. So just if we seem like we're getting off schedule, don't worry about it. I'll take care of everything. It'll work out in the end. Okay? I'm trying to reassure myself as much as you right now. So, hardware versus software. This will be a nice, nice baseline to start with. Hardware is a collection of physical, electrical components that comprise a computer's physical form. Software is a series of instructions stored in a computer's memory that may be executed by sometimes arbitrary software systems. A processor is a group of circuits that implement operations on memory. These operations are known as instructions or hardware instructions. So, one of the things that we're going to do over the course of this of 2MP3 is we're going to be much more interested in investigating the interface between software and hardware than you probably will have seen so far. This is due to a number of different factors. C is a very low-level programming language, which means that the instructions that you are programming with in C are much more similar to the underlying hardware instructions that they get compiled to than in, for example, Python. Or if you've used other programming languages like Haskell or C# or C++ or Java or any of those types of languages. C is it's getting very close to bare metal programming or bare wire programming. It's like that, but you also have an operating system to support you. So, yeah, the hardware-software interface is something that we're going to be investigating. We're going to have to know things like, how does the CPU execute instructions? How does the CPU load memory? Obviously, we're not going to get into like the details of the electronic circuits, but we're going to need to know things at a sort of abstract or conceptual level in order to use these types of ideas to effectively program in C. So, programming languages are more or less abstract depending on how directly they access a system's underlying hardware. In high-level languages, such as Python and Haskell, an operation may represent many hardware instructions. This is particularly true of something like Haskell, where you are shifting paradigms from in terms of CPU instructions, the underlying hardware instructions. These are in an imperative programming paradigm, right? It's imperative programming. Assembly is an imperative language. When you have something like weird and abstract, like a functional language, writing one line in Haskell might mean that you have generated 1 or 200 assembly level instructions. Whereas in C, there is a much more compact the number of hardware instructions that an operation in C represents is going to be far, far, far fewer. It's sort of complicated by the fact that expressions can be as long as you want, but in terms of like the control structures of C, you're going to maybe 5 or 10 lines in assembly for everything that you do. So this is why C is known as a low-level language. High-level languages are abstract languages. Low-level languages are concrete languages. High and low refers to the level of abstraction. So, different languages are good for different things, and a good developer knows which languages are suited to which applications. So, if you want to do something abstract that has to do with abstract algebras or, something involving excessive string manipulations, a language like Haskell will allow you to develop a program in a fraction of the time that developing in C will allow you to do. However, if your application is something where efficiency is the name of the game, the code efficiency, then you're probably wanting to use a lower level language like C. There's a very famous example of the use of low-level languages in order to make a program more efficient. Does anybody remember Rollercoaster Tycoon? It's an old game now. It's from the 90s, but it's possible that you guys will have seen references to it. Rollercoaster Tycoon did something that there was a technical innovation there that had not been seen in video games that far. Prior to so in Rollercoaster Tycoon, you make a little theme park, and these little NPCs are walking around the theme park riding on your roller coasters, and they all have stats like how nauseated they are and how hungry they are and how much they have to go to the bathroom. And the thing about Rollercoaster Tycoon was that you could have, at the time, about 1,000 of these guys walking around. This was completely unheard of at the time, that you would have 1,000 simultaneous AIs running around a virtual environment in the context of a game that was supposed to run on ordinary people's computers. Like, we weren't talking about a supercomputer here, right? So, hey, you're from 1MD3. This isn't your course. Get out of here. Yeah. Zoo Tycoon. Actually, my wife really likes Zoo Tycoon. It was the Microsoft version. It's kind of funny. Very, very poorly optimized, that game. It's kind of interesting. There's a hard cap in that game of how many NPCs you can have running around, because Microsoft was not as good at optimizing as Rollercoaster Tycoon was. Actually, there's a way to in that game, if you modify the config files, you can remove the cap of how many people can be in the theme park, be in your zoo, and you can get up to really stupidly high numbers, but you have to constantly be saving the game, because the game will crash, like hard crash, randomly, like every couple of minutes. It's kind of hilarious. Anyway, the way that Rollercoaster Tycoon was able to have all of these NPCs walking around was because that game has portions of it optimized in assembly programming. So assembly programming is even lower level than C programming is. But without having optimized that in assembly, they would never have been able to achieve that level of technical finesse. But anyway, so when we're programming in C, we are in the low abstraction end of the pool of languages. So, why would you want to learn a low-level language? Because it's a required course, that's why. No. Don't think that way. That's a bad way to think about your education. So, low-level languages have applications. Some non-traditional programming environments, such as microcontrollers, do not even support high-level languages. Python is sort of creeping into everything, as it has a tendency to. But if you think about it this way, a microcontroller is a single chip, right, that has on it all of the memory and the CPU that is required to have a independently functioning programmable computer-like object in a chip. So you'll get to do these in third year, I believe. 3TA 4 is a course in microcontroller programming. So, or at least it used to be. When you have a whole computer that's been stuck onto a chip, the amount of memory that's available for that thing, there are a couple of factors that go on. Number one, it's never going to be big, just because the size of the physical chip object itself isn't very large. And, this has been somewhat ameliorated by the fact that, flash memory is getting very, very small. Micro SD cards are pretty cool and awesome, but you have to think of the memory that a microcontroller needs as being even smaller than a micro SD card. So, your memory limited. One of the traditional trade-offs that high-level languages make in order to make your life easier is to require more memory. So in C, we are requiring very, very little memory, which means that our C programs can fit on very tiny, minuscule little computers. So that's a good thing, because that makes it possible. There's another angle to be considered there, too. Let's say that you, as an engineer, are designing a product. And let's say that product uses a microcontroller. Let's say this product is going into mass production. Generally speaking, a microcontroller will be more expensive the more memory it has on board. So, if you, as a clever programmer, can chop down the amount of memory that your program requires, that reduces the requirements on the microcontroller, which means that possibly a cheaper, a less expensive microcontroller could be used for the same application. If you're working for a big company, let's say you're making kitchen timers, right? If you can fit let's say that you can save 10 cents per kitchen timer that your company manufactures by not having as great a memory requirement. If you are saving 10 cents per timer and your company manufactures 1 million timers, in chat, how much money have you saved your company? And, these are the types of things that companies love to do. They love to save money like that. So, optimization. Because they use a small number of hardware instructions per operation, programs written for low-level languages can be very small and run very quickly relative to high-level languages. Some optimizations are not even possible in high-level languages. So, think about your operating system for a moment. There are some routines in your operating system that get run, $10,000. They get run, maybe? Or is it $100,000? Anyway. Math numbers. If you're... what was I saying? Jesus Christ. Yes, so in your operating system, if you have a operation that is executed, say, 500 times a second. And there are definitely operations in your operating system that would be on that level. Let's say that you could save 4 CPU instructions per operation. You know, on something, yeah, I think it is 100K. Thank you. On something, like, yeah, so if you make an improvement like that, you have just made your salary for it back for your company, right? So I should try to think of one thing at once, eh? And essentially, you can make a very similar argument to the amount of money you're saving your company on digital timers to the amount of time you're saving an operating system by improving the efficiency of very frequently run tasks. That's why the majority of I believe the majority of Linux is written in C. Although I'm sure somebody's going to pull up statistics that'll prove me wrong on that. Also, knowledge. So, an appreciation for what our programs are doing under the hood will make us better programmers. Unless you understand how memory works, you'll never master it. Unless you understand what the CPU is doing, you'll never master it. Taking this course will allow you to understand what's going on in memory transactions. This will allow you to deepen your understanding of all programming languages, not just C. Learning C is great because it teaches you all kinds of stuff about a large class of languages. Anyway, so that's why you should be learning this. Let's just review some key concepts right now. You guys hopefully will have seen the von Neumann architecture in 1D04. You can let me know if this is new for you. Please let me know if this is new for you guys. But you already know this. It's just applying a name to it. The von Neumann architecture is the model on which all of our CPU-based computers operate. You've got an input device, and you've got an output device. Input devices are things like keyboards and mice. Output device, or in the case of a microcontroller, these can be electrical signals. Output devices, monitors, printers. In the case of microcontrollers, these would be more electrical signals. These would be pins. The CPU, or central processing unit, has 2 subunits inside of it. You've got the control unit. That makes sure that the data is in the right place to be operated on. And you've got the arithmetic logic unit. This is the bit that actually performs the calculative operations on memory. The central processing unit interacts in various ways with the memory unit. The memory unit is the thing that stores memory. A lot of the time, you sort of are very hand-wavy about how memory actually works. But in this course, we're going to get into it a little bit. Probably, not as much as some, like if you were taking computer engineering, you would get into it more. But we're gonna learn enough about it to be able to program effectively in C. So, let's talk about memory. You'll probably have heard these terms before. Computer memory can be stored in many ways. You've got 3 primary categories. You've got ROM, or read-only memory. This is your system's permanent data storage. The files in your file system are stored in ROM. Physically, this is normally a magnetic drive, a solid-state drive, or flash memory. Basically, this is non-volatile memory. This memory stays put if your computer is powered down. That is another good way of thinking about it. You also have RAM, which is random access memory. This is your system's working memory. On execution, programs are loaded into the RAM from the ROM, if they're stored in the ROM. when, like, you know, RAM chips, you guys should have an idea that, you know, when you're buying your laptop and it says it has, 8 gigabytes of memory, the type of memory they're talking about is RAM. When they say 2 terabyte SSD, they're talking about ROM. Registers. This is a type of memory that's not in the rundown of features that your laptop will have when you buy it. Registers are memory storage internal to the CPU. Data must be loaded into the registers in order for the CPU to perform operations on it. So, is this the same ROM as in a video game ROM? Yeah, I believe that's... I might be BSing you a little bit when I say this, but yeah, I believe that when you download like a ROM for Mother 3, what you're doing is you're downloading the read-only memory that constituted that game, right? It's because, the game will have a lot of different files, and a whole directory structure inside. But what you're doing is you're sort of taking a wholesale rip of the entire read-only memory for that game, right? Anyway. So, so this is roughly. Let me see what the next. Yeah, okay. This is roughly how memory is loaded and how it's operated on. A program is stored in read-only memory. The computer, on executing it, loads it into the random access memory. The random access memory is then bits of it are picked up and put back by the CPU. It's the process of having a program is picking pieces of data out of the RAM, loading them into the registers of the CPU, operating on them, and then putting them back in the RAM. That is the only thing that computers do. Everything else is fluff. Everything else is interpretation. So, one might ask, why doesn't the CPU just deal with the RAM or the ROM directly? Why are registers necessary? And the answer to that is, as you go down this list, the memory gets faster and faster. So, read-only memory is slow. It's permanent, but it takes a long time, relatively speaking, in order to get data out of it. RAM is a lot faster, but it's still not as fast as the registers. So, the reason that you want to be operating with the registers in the CPU is because they're the fastest thing. Yeah, which is good because there are far more register memory swaps that occur than either of these two. For reasons that we'll see. Cool. We'll see that when we get into assembly programming. When you program in assembly, you are actually directly manipulating registers, whereas in most other cases, like in C programming, you don't really get into registers specifically. You do indirectly, but we'll get into that. Are registers like the cores of a CPU? It's the core memory of a CPU. The CPU, again, is comprised of control unit and arithmetic logic unit. The control unit is using the registers. The control unit is using... It's executing instructions on how to manipulate the memory in registers, load the registers, unload the registers, etc. The arithmetic logic unit is saying, put in register 3 the results of adding register 1 to register 2. That's what the arithmetic logic unit is doing. Yeah, cache memory is something else. Yeah. So again, I'm dealing with I'm kind of dealing with high-level abstractions, but cache memory is another type of memory. It's kind of halfway between the RAM and the registers. Cache is faster than RAM. and it is not as, like, the registers are important because they're hooked up to the arithmetic logic unit. The cache is not hooked up to the arithmetic logic unit. The registers have to load data in from the cache in order to operate on it, but that's an even faster operation than loading from RAM. So it's like, it's in between stuff. And if it wasn't useful, it wouldn't be there. That's kind of how the creation of computer systems works. That was a good question. Thank you very much. I love good questions. So, just to review some very basic concepts. The data that we access in system memory can be categorized hierarchically. So the smallest unit of memory is a bit. They are either a 1 or a 0. They are the atomic unit of memory. There is nothing smaller than a bit. They are the atoms of our digital universe. A byte is made up of 8 bits, and it's as simple as that. Word is a little bit, what a word is kind of different. It varies by the CPU architecture. So it is a word for a CPU is the number of bits the CPU's instruction sets operates on in a single operation. Another way of saying that is it's the number of bits that are contained in the registers in the CPU. For example, the Nintendo Entertainment System was an 8-bit machine, so the words and the bytes were the same size, right? A byte is 8 bits, so a word was 8 bits. So for the NES, there was no distinction between words and bytes. For the Nintendo 64, that was a 64-bit machine, as you might have gathered from the name. So a word was comprised of 8 bytes. This is also, coincidentally, how many bits or bytes a floating point number is, which, floats are a whole thing. We're going to get into them. But, yeah. Anyway, any questions so far? Hopefully everything's reasonably cogent so far. So this is one of the few occasions where I actually use something from the textbook. You can have... So the data hierarchy can be like this. You can have bits that are contained in characters, which are contained in fields, which are contained in records, which are contained in files. We'll get into fields, records, and files later on in the course. So a character is, generally speaking, it's encoded as either 8 or 16 bits. A computer's character set is used to write programs and represent data. So characters are just integers they're just, arrangements of ones and zeros. The way that the arrangement of ones and zeros that's contained in the character gets interpreted as a character is by filtering it through the computer's character set. The character set may be different depending on which computer you're working with. Although, generally speaking, these days, pretty much everybody's using the same. Like, these things may not have been standardized in the 80s, but they sure as hell are standardized in the year 2020, at least for most systems. So C supports various character sets, including ASCII, UTF-8, and UTF-16. Generally speaking, when you have a character data type in C, that is 8 bits. And we're going to get into we're going to get into the basic data types in the next topic, not in this topic, but the next one. Fields are composed of characters or other data types. They associate data with a context in order to establish meaning. Records are collections of fields. This is, if you know any C going into this, that we're talking about structs right now, or structures. A file contains an arbitrary amount of data in an arbitrary format. In some operating systems, although there are some commonalities which are necessary in order for it to be considered a file. In some operating systems, a file is viewed simply as a sequence of bytes, an organization of the bytes in a file, any organization of the bytes in a file, such as organizing the data into records, is a view created by the application programmer. Databases, a collection of data organized for easy access and manipulation. We're not really going to talk about databases, but it's like this is the context of data. The most popular model is the relational database, in which data is stored in simple tables. A table contains a number of records, which contain a number of fields. Again, if you want to learn databases, it's an extremely useful thing to learn. If you get a technical elective, I highly recommend learning databases because it's an extremely employable skill, even for a robotics engineer. So, the time is currently 12:20. That is, I think we'll conclude there. So I got through 8 slides. All right. I don't know. Can you guys? I'd like a little bit of feedback on the lecture today, if you guys wouldn't mind. Do you feel the pace was good? Do you feel the slides were interesting? Particularly, I'm interested in what you guys thought of the pace. Was I going too fast? Was I going too slow? Please let me know in the chat. But yeah, we're gonna call the lecture here. Next time we will talk about. Oh, geez. Oh, you saw the comic. Oh, you saw the other comic. Oh, now you know there are 2 comics. So we're going to talk about C, the C programming language, next time, which will be, I think, Tuesday. Okay. So, part of the reason that I'm just now thinking of this, part of the reason that the pace, you guys probably were thinking the pace probably seemed slow in this one because I'm talking about stuff you guys already know, you know? But I have to, believe it or not, there are probably some people in the class who don't remember anything about von Neumann architecture. So, during the first lecture, that may not be a great time to get a feeling of, it's more like the speed I was talking at. I think the how interesting the slides are has something to do with it. Speed up the space during some slides. Okay. Cool. Well, okay, so let's do this then. If you guys feel that I'm going too slow, please say something in the chat. Speed this up. Come on, we got things to do. Because it's just kind of my lecture style to insert a bunch of elaboration on the things that are on the slide, not just read the slide to you, because it's terrible when people just read the slides. But if you guys would, ask me to speed up when it's getting a bit boring, I think that would be 1 million subscribers. Yeah. I only need 700 more, and then I can monetize the channel. Yes, okay. Okay, yeah, so please give me feedback during the lecture as well. That'll help me. It's kind of tough when you don't actually have an audience. I'm really used to normally having a room full of people because, if you're giving a lecture and you can look out amongst the crowd and see that everybody is asleep, you can say, okay, maybe they already know this, But, get that gold play button. Yeah, we'll see. Also, stop and check to see if everybody understands 1 or 2 examples so you can move on. Yeah, okay. Yeah, we can do that too. So, the whole purpose, I really like the YouTube chat because it can make the lecture a little more interactive. Like, I can look at the statistics, actually. If you guys take a look at the chat right here, you can see that I'm getting pretty much no comments through most of it, just kind of at, 7 minutes at intervals. So, these lectures can be as interactive as you like. Chop chop works, yeah. Yeah, oh yeah, sorry. You guys probably have a class to get to. So, yeah, okay. We will resume on Tuesday. Thank you very much for your time and attention, folks.